Have you ever stopped to think about just how fast you can think? Well, it turns out the information superhighway inside your own body is faster than a high-speed train, hitting an incredible 268 miles per hour. So how in the world does that actually work? Let's dive in.
No, really, just take a second. Imagine someone taps you on the shoulder. That feeling, the decision to turn your head, it all feels completely instantaneous, doesn't it? But what's actually happening inside your body to make that split-second reaction possible? Well, the secret is all about pure, unadulterated speed. Get this. At its absolute peak, a nerve impulse can travel at a mind-boggling 268 miles per hour. That is faster than a Formula One car going flat out. And this biological superhighway is running inside you, right now. So how on earth does our body pull off that kind of velocity? To understand the speed, we first have to meet the absolute star of the show, the neuron. These are the fundamental cells of your nervous system, the basic wiring that connects, well, everything, from your brain all the way down to your fingertips.
So if you just look at a neuron, it's structured a lot like a biological wire, right? You got the cell body, which is kind of like the command center. Spreading out from it, you see the dendrites, and those act as receivers. And then there's that one main output cable, the axon, that sends the signal on its way. Let's break those parts down. The whole journey of a message kicks off right here at the dendrites. You can think of them as the neuron's antennas. These super intricate branch-like arms are constantly listening, picking up signals from literally thousands of other neurons around them. Okay, so once the dendrites and the cell body collect enough of a signal to say go, the message gets fired down this long cable, the axon. This is the transmitter. It's designed to carry that electrical signal over a distance, sometimes a really, really long one. And how it does that is the key to this whole story. Now, the signal itself isn't like electricity just flowing through a copper wire. It's way more clever than that. It's this self-regenerating pulse of energy. It's called the action potential, and it is the universal language for the entire nervous system. So what exactly is an action potential? Well, you can think of it like a wave of electricity. It's this super fast temporary flip in the electrical charge of the neuron's membrane. This little spark is the fundamental piece of information. It's basically the 1 or the 0 in our biological computer. Here's how that little wave actually works. At rest, a neuron is negatively charged on the inside. But when a stimulus hits, these little gates for positive sodium ions fly open. They rush into the cell, flipping the charge to positive. That's the spark, the depolarization. And then, immediately after, different gates open for positive potassium ions, letting them rush back out to restore that negative balance. This in and out flow creates a wave that moves itself all the way down the axon. And this brings us to a really important rule. The action potential is all or none. A neuron doesn't fire a weak signal or a strong signal. It either hits the threshold and fires at full power, or it just doesn't fire at all. It's like a light switch. It's either all the way on or all the way off. There's no dimmer. Okay, so we've got our signal, but how does it travel? Well, it turns out there are two main methods. And the first one, well, it's the slow lane of the nervous system. It's called continuous conduction, and it happens in axons that don't have any insulation. In these bare, unmyelinated axons, that whole domino effect we just talked about has to happen at every single spot along the way. The spark in one little segment triggers the next, which triggers the next, in this continuous, unbroken wave. It works, for sure, but as we're about to see, it is not very fast. And the numbers really tell the story here. These unmyelinated fibers transmit signals at just over 2 miles per hour. That is literally a walking pace. For things like sensing a gradual change in temperature, that's fine. But for pulling your hand away from a hot stove, that's dangerously slow. So how did biology solve this major speed problem? With a totally brilliant upgrade: insulation. This leads to an incredibly fast and efficient way of sending a signal called saltatory conduction, which literally means to leap. This game-changing upgrade is a fatty substance called myelin. Specialized cells wrap the axon in these thick layers, creating an insulating sheath. And it works just like the rubber insulation on an electrical cable. It stops the electrical current from leaking out and fizzling away over distance. And this is where the magic happens. The myelin sheath isn't one solid piece. It has these little uninsulated gaps, called the nodes of Ranvier. So a full action potential gets generated at one node. The current then flows super fast under the insulated part to the next node,
where it's strong enough to trigger another full action potential. The signal effectively leaps from node to node at an incredible speed.
This just lays it all out side by side. You've got the slow, continuous wave that has to rebuild itself at every single point, which, by the way, burns a ton of energy. And then you have the high-speed leap, where the signal only has to be regenerated at those nodes, so it's not just way faster, it's also way more energy efficient. Okay, so we have this amazing high-speed system. But so what? Why is it so important? What's the big payoff for evolution investing all this energy into building this insulated, high-speed network? I mean, just look at the impact of myelination on this graph. We go from an unmyelinated fiber at a measly 2 miles per hour all the way up to a thickly myelinated one hitting that top speed of 268. This isn't just a small improvement. It's a revolutionary leap in what a biological system can do. And this is why it all matters. This is what enables the rapid-fire reflexes that save you from getting hurt. It's what allows for complex, coordinated movements when you're playing sports or an instrument. It's the speed of thought itself. And here's the kicker. This whole high-performance system is so efficient that it runs everything on just about 20% of your body's total energy budget. Amazing. You know, the vital importance of this myelin insulation becomes tragically clear when you look at diseases like multiple sclerosis. When that myelin sheath gets damaged, that high-speed jumping we talked about starts to fail. Signals slow down, they get garbled, or they just stop altogether. It's a stark reminder of just how essential this incredible system is for everything we do. So, from a simple chemical spark to a perfectly insulated biological superhighway, our nervous system is just an absolute marvel of engineering. It solved the problem of fast, efficient, long-distance communication millions of years ago. It really just leaves you wondering, what's going to be the next great leap?